Okay, we're streaming. That was an accident. I didn't mean to do that. It's whatever. Welcome to Bite Me. My name is Jillian. I'm going to be your host. And today we're going to be squashing bugs one bite at a time. Alright, so we went through chapter 6 yesterday, or the end of chapter 6 yesterday. Today we're going to do chapter 7, which is packages, crates, and modules. I've actually... Now we're better. I've actually never read this chapter before. And any following chapters I haven't read either, so this is going to be the first time I've ever reading this. And let's do it together. I'm so excited. Also, I have my mini Rust series. I think chapter 4, 5, and 6 are coming out this week, so I'm going to be recording those today. And stay tuned for those. Those are going to be following the chapters. Chapter 2, 3, 4, 5, and 6 are going to be out. So you can try my project mini series. It's just a basic understanding of what we're learning within the Rust book. So, all right, let's jump in. Okay, so we're on packages and crates and modules. Okay, as you write large programs, organizing your code will become increasingly important. By grouping related functionality in separate code with distinct features, you'll clarify where to find code that implements a particular feature and where to go to change how the feature works. The programs we've written so far have been in one module in one file. As our project grows, you should organize code by splitting it into multiple modules and then multiple files. A package can contain multiple binary crates, and optionally one library crate. As the package grows, you can extract parts into separate crates that become external dependencies. This chapter covers all of these techniques. For very large projects comprising a set of interrelated packages that evolve together, a set of interrelated packages that evolve together, Cargo provides workspaces we'll cover in Cargo Workspaces in Chapter 14. We are actually almost halfway through, even though we're in Chapter 7, we're almost halfway through this series, and I'm super excited. Oh, I'm so excited. Okay, we'll also discuss encapsulating implementation details, which lets you reuse code at a higher level. Once you've implemented an operation, other code can call your code via its public interface without having to know how the implementation works. The way you write code defines what parts are public for other code to use and which parts are private implementation details that you reserve and write to change. This is another way to limit the amount of detail you have to keep in your head. Before I keep going, I just want to make sure that I'm live on Twitch. Okay, perfect. I'm just starting to learn how to use Twitch, so this is my second live on Twitch. This is my 10th episode on YouTube, so this is very exciting stuff, for me at least. Okay. A related concept in scope is scope. The nested context is which code is written has a set of names that are defined as in scope. When reading, writing, and compiling code, programmers and compilers need to know whether a particular name at a particular spot refers to a variable, function, struct, enum, module, content, or other item, and what that item means. You can create scopes and change which names are in or out of scope. You can't have two items with the same name in the same scope. Tools are available to resolve name conflicts. Rust has a number of features that allow you to manage your code's organization, including which details are exposed, which details are private, and what names are in each scope in your programs. These features sometimes collectively referred to as a module system, including packages, crates, modules, and paths. I'm just going to give you a second to read those because actually, alright. In this chapter, we'll cover all these features, discuss how they interact, explain how to use them and to manage scope. By the end, you should have a solid understanding of the module system and be able to work with scopes like a pro. Exciting. This one is going to be, I'm thinking it's going to be pretty long. It's got 5 different, or 5 separate chapters. So this might be like a 2-parter. We'll see. Let's see how it goes. So packages and crates. The first parts of the module system we'll cover are packages and crates. A crate is the smallest amount of code that the Rust compiler considers at a time. Even if you run rustc rather than cargo and pass a single source code file, as we did all the way back in Rust Programming Basics in Chapter 1, the compiler considers that the file to be a crate. Crates can contain modules, and the modules may be defined in other files that get compiled with the crate, as we see in the coming sections. Okay, so I'm trying to understand these as well. So I'm just going to break it down in my brain as best as possible. I'm just going to say what I'm thinking out loud as we go through the chapters, okay? A crate can come in one of 2 forms, a binary crate or a library crate. Binary crates are programs you can compile to an executable that you can run, such as command line program or server. Each must have a function called main that defines what happens when the executable runs. All the crates we've created so far have been binary crates. Okay. Library crates don't have a main function and they don't compile to an executable. Instead, they define functionality intended to be shared with multiple projects. For example, the RAN crate we used in Chapter 2 provides functionality that generates random numbers. Most of the time, when Rustaceans say crate, they mean library crate, and they use crate interchangeably when the general programming concept of library. So, the crate root is a source file that the Rust compiler starts from and makes up the root module of your crate. We'll explain modules in depth in control scope and privacy with modules. A package is a bundle of one or more crates that provides a set of functionality. A package contains a cargo.toml file that describes how to build those crates. Cargo is actually a package that contains the binary crate for the command line tool you've been using to build your code. Okay. Okay. So within the cargo.toml file, a lot of the time, that section where it says dependencies, those are where we put our packages. That's what it's trying to say. So like when we need a new library crate or we need a crate that's external, we put it in, package, we put it in dependencies or under dependencies. Cargo is also a package that contains the binary crate for the command line tool that we've been using to build our code. So the cargo package also contains a library crate that the binary crate depends on. Other projects can depend on cargo library crate to use the same logic that cargo command line tools use. Okay. All right. So we have like the lowest. I guess like the lowest of our tiers is our binary crate or crate. Is the smallest amount of code that the Rust compiler considers at a time. So there's a crate, and then we have binary crates, and we have library crates. Binary crates are the ones that need a main function to execute, and then library crates do not need a main function, but they say that those library crates, I'm thinking, Okay, so generates random numbers. Okay, so we did use it in chapter 2. We use a library crate with a standard input output crate, I think. So that's what we put in our dependencies. I'm gonna keep reading. Hopefully it clicks with like in my brain as well as yours. Oh, okay, and then we have a package. Package is a bundle of one or more crates in the functionality, and that's what we put in the dependency. Right. Okay, so that's in the cargo.toml file, and I think that's what we're gonna put in our dependencies area, where we're using a package. Okay, so a package can contain as many binary crates as you'd like, but at most one library crate. A package must contain at least one crate, whether that's a library or binary crate. Okay, so let's walk through what happens when we create a package. First, we enter the command cargo new my project. So cargo new my project, binary crate. Then we have my project package. We're gonna list what is in my project, which is just a cargo.toml and source file. And then we go into the source file, and then we have our main.rs. So with binary, we'll automatically create a main file, essentially. After we run cargo new my project, we use the ls to see what cargo creates. And the my project directory, there's a cargo.toml file giving us a package, okay, which is source. There's also, oh, it's giving us a package. Okay. There's also a source directory that contains the main.irs file. Open cargo.toml to your text editor and note that there's no mention of source/main rs. Cargo follows the mention that source/main rs is the root crate of the binary crate with the same name as the package. Likewise, cargo knows if the package directory contains source/librs, the package contains a library crate with the same name as the package. And the source/librs is a crate root. Cargo passes the crate root file into the rustc to build the library or binary. Okay. Alright, I'm gonna keep going. Here we have a package that only contains source/main rs, meaning it only contains a binary crate named my project. Okay, so if a package contains source/main rs and source/librs, it has two crates, a binary crate and a library crate, both with the same name as the package. A package can have multiple binary crates by placing files in source/bin directory. Each file will be separate binary crates. So essentially, and this is what I did for my project series, my mini project series, within the source file, I created a bin file, which will let me separate my projects into mini projects. So once you run or do a cargo run, you do a --bin, and then put the file name that you're trying to execute, and it will execute separately as a binary crate. Hopefully that makes a bit more sense. If you do follow my mini Rust series, you will see this and you can do it yourself, and you'll understand what I'm talking about, especially when we're talking about these crates. Okay, so we have control scope and privacy with modules. So in this section, we'll talk about modules and other parts of the module system, namely paths, which allow you to name items. The use keyword that brings a path into scope, and the pub keyword to make items public. We'll also discuss the as keyword, external packages, and glob operator. Okay, so when they're talking about paths, we've used or brought into scope or imported different crates, different packages within. I'm pretty sure it would be known as a crate. I think that's what it was saying within the last section where we are importing crates, but we use the use keyword to import them. Pub keyword, I know that I think all of our items are, just as they're immutable, they'll also be private, so you have to make them public. The as keyword I've used in previous projects. It's also, it's like an alias name that you give someone or give something. External packages, we've used external packages before. I've never heard of the glob operator, so that's a little bit new to me. Taking my water break a little bit earlier today. I just didn't drink any water today. I'm very thirsty. Okay, module cheat sheet, okay? Before we get into the details of modules and paths, here we provide a quick reference on how modules, paths, and the use keyword. Oh, sorry, my fan is on. Sorry. Turn on my fan. Okay. Where was I? Okay, before we get into the details of modules and paths, here we provide a quick reference on how modules, path, and the use keyword and the pub keyword work in the compiler, how most developers organize their code. We'll be going through examples of each of these rules throughout this chapter, but this is a great place to refer to as a reminder of how modules work. Alright, so start from the crate root. When compiling a crate, the compiler first looks in the crate root file, usually source/librs for a library crate and source/mainrs for a binary crate for code to compile. Okay. Now declaring modules, in the crate root file, you can declare new modules. Say you declare a garden module with mod garden. The compiler will look for the module's code in these places, in line with curly brackets that replace the semicolon following mod garden, in the file source/garden.rs, in the file source/garden/mod.rs. Okay. Now I'm kind of confused as to what a module is, like in relation to the lib or binary crates. But wait, hold on. Before we get into details of modules, so I guess a module is just a path. I'm kind of confused. Okay, let's keep reading on, okay? Declaring submodules. In any other file than the crate root, you can declare submodules. For example, you might declare a mod vegetables in source/garden.rs. The compiler will look for the submodule code within the directory name for the parent module in these places. So inline directly following mod vegetables within curly braces instead of a semicolon. Curly brackets instead of a semicolon. In the file source/garden/vegetables.rs, in the file source/garden/vegetables/mod.rs. That's what I'm a little bit confused about. What is this mod.rs? And why is it so different? You know? Is this name? Paths to code in modules. Once a module is part of your crate, you can refer to the code in that module from anywhere else in the same crate, as long as the privacy rules allow, using the path to the code. For example, an asparagus type in the garden vegetables module would be found in crate : garden : vegetables : asparagus. Now, private versus public. Code within a module is private from its parent modules by default. To make a module public, declare pub mod instead of mod. To make items within the public module public as well, as use pub before their declarations. Okay, the use keyword. Within a scope, the use keyword creates shortcuts to items to reduce repetition of the long paths. In any scope that can refer to crate, : garden, : vegetables, : asparagus. You can create a shortcut with use. And from then on, you only need to write asparagus to make use of the type in the scope. Okay. I've used use before. I've also used a mod, but the way that they're explaining it is confusing me. I guess because the submodules. This is the cheat sheet, so we haven't even really talked about modules like that. Here we create a binary crate named backyard that illustrates these rules. The crate directory, also named backyard, contain these files in directory. So we have our top of our file or tree, backyard, which contains cargo.log, cargo.toml, and source. And within source we have garden RS, and main. Within our garden folder we have vegetables.rs. So the crate root file is source/main rs, and it contains use crate garden vegetables asparagus. So we're going within this file vegetables to find asparagus, and then pub mod garden. See, this is what's confusing me, this pub mod, this module, I guess garden, which is within source, so I guess the module would be the file, the folder that it's hosting vegetables in. Then we have function main rs let plant to bind to asparagus, which is in the vegetables module. Print line, I'm going to plant, and we do it in pretty print. Okay, so the pub mod garden line tells the compiler to include a code that finds in source/garden.rs. Okay, so yes. Oh, it's in source/garden.rs. Oh, okay. So is this the submodule? Why are we using crate, and why are we using pub mod? These are the things that are confusing. You see all these lives, I'm getting so confused, and it's just literally me like reading, and I haven't read this in a long time, so it's me like gaining this knowledge back. Okay, pub mod vegetables. Here, pub mod vegetables means that the code in source/garden/vegetables.rs is included too. The code is derive bug pub struct asparagus. So now let's get into details of these rules. I just want to know, what is a module? Like, what is, and you know what? Maybe it was on the first page. So let's go back. What are my modules cheat sheet? We're in grouping related modules. Okay. Let me just go back to see what it says. Modules let you control the organization, scope, and privacy of paths. Interesting. Let's read on. My confusion will not stop this stream. Modules let us organize code within a crate for readability and easy reuse. Modules also allow us to control the privacy of items because the code within a module is private by default. Oh, okay. Private items are also internal implementation details not available for outside use. We can choose to make modules and the items within them public, which exposes them to allow external code to use and depend on them. Okay. As an example, let's write a library crate that provides the functionality of a restaurant. We'll define the signatures of function, but leave their bodies empty to concentrate on the organization of the code rather than the implementation of the restaurant. In the restaurant industry, some parts of the restaurant are referred to as the front of the house and others as the back. Front of the house is where the customers are. This encompasses where the hosts seat customers, servers that take orders and payments, and the bartenders make drinks. Back of the house is where the chefs and cooks work in the kitchen, dishwashers clean up, and managers do administrative work. To structure our crate in this way, we can organize the functions into nested modules. Create a new library named restaurant by running cargo new restaurant --lib. Then enter the code in the listing 7-1 with source/librs to define modules and function signatures. This code is the front of the house section. File name source/lib. Okay, so we have mod front of house. Then we have mod hosting with the function add to list, function seat to table, mod serving, function take order, function serve order, function take payment. Okay. Now we define the module in the mod keyword, followed by the name of the module. In this case, front of the house. The body of the module then goes inside curly brackets. Inside modules, we can place other modules, as in this case of the module hosting and serving. Okay. I'm confused as to why this is different than the use statement. I understand that is private, so we can use the mod statement if we want to make it public or in scope. But why is use and mod so different? That's my real question right there. I'm gonna finish reading this and then we're gonna ChatGPT this because I feel like I should use ChatGPT a little bit more on these streams. I usually do it after if I have a question, but I want to utilize the book to its fullest potential when I'm on these streams. So it seems more, I don't know, I think it seems a little bit better to try and figure it out while I'm here. Alright. Okay, so, where did we go? By using modules that group related functions together and name why they're related, programmers using this code can navigate the code based on the groups rather than having to read them through all the definitions, making it easier to find definitions relevant to them. Programmers adding a new functionality to this code would know where to place the code to keep the program organized. Earlier, we mentioned in source/main.rs and source/librs are called crate roots. Now, the reason for their name is that the contents of either of these two files form a module named crate at the root of the crate's module structure. This is known as a module tree. So, okay. So they're using the module as a path and also as a name for the structure of the files or folders. So this tree shows how some of the modules nest inside other modules. For example, hosting that's inside the front of house. The tree shows how some of the modules are siblings, meaning they are defined in the same module. Hosting and serving are siblings defined in front of the house. So is a module technically a folder? Because it is a path? Because it's like showing a path of, let's keep reading and then I'm going to ChatGPT it while we're here. If the module A is contained inside module B, we can say that module A is a child of module B and that module B is the parent of module A. Notice that the entire module tree is rooted under the implicit module named crate. Now the module tree might remind you of the file system's directory tree in your computer. This is a very apt comparison. Just like directories in a file system, you use modules to organize your code, and just like files in a directory, we need to find our modules. Okay. So it's just a file system, an easier way to file your files as a system. I do want to just ask Claude an easier way for understanding what it is. I think my question was, what was this mod RS really? So it's saying that basic unit is a module declared with mod. Okay, so it's saying that it's organizes code into namespaces. Okay, instead of writing everything in one RS file, Rust lets you spit a module out, so you have a module network in their main file. What? Okay. So mod is a bit of a older naming convention system. You're allowed to name the file network.rs, okay, and have the sibling in a folder. Okay. Yeah, okay, so that's what's confused. It was saying that the mod.rs file within whatever folder that you're going to put it in is kind of an older style naming convention because if you have mod.rs and so many different folders, it's just going to be so complicated because they're all named mod.rs. That's what my real question was. Alright, we're going to keep going. Thank you, Chad. What is this? Claude. He's my best friend. I love him. Alright, paths to referring to an item in a module tree. To show Rust where to find an item in a module tree, we use a path in the same way that we use a path when navigating a file system. To call a function, we need to know its path. A path can take two forms. An absolute path is a full path, starting from the crate root for code from the external crate to the absolute path. The absolute path begins with the crate name, and for the code from the current crate, it starts with the literal crate. Okay, and then a relative path starts from the current module and uses self, super, or an identifier in a current module. Okay. Both absolute and relative paths are followed by one or more specifiers separated by double colons. Now, returning to listing 7-1, say we want to call the add to waitlist function. And this is the same as asking what's the path of the add to waitlist function. Listing 7-3 contains listing 7-1 with some of the modules and functions removed. We'll show two ways to call add to waitlist function from the new function, eat at restaurant, defining crate route. Now these paths are correct, but there's a problem, remaining that it will prevent this example from compiling as is. Okay, we'll explain why in a bit. The eat at restaurant function is part of sometimes my that's crazy. Okay. The eat at restaurant function is a part of the library's Crate public API, so we'll mark it as pub keyword. Now, in the exposing paths with pub keyword section, we'll go into more detail about pub. We have mod front of house, mod hosting, then we have function add to waitlist. Pub function eat at restaurant with the absolute path for crate. Remember, absolute path starts with crate. Front of house, hosting, add to waitlist. And then we have a relative path, which is front of house, hosting, add to waitlist. So we didn't need to put crate for a relative. Now, the first time we call add to waitlist function in eat at restaurant and function eat at restaurant, we use an absolute path. The add to waitlist function is defined as the same crate as eat at restaurant, which means we can use crate word to start the absolute path. When we then include each of the successive modules until we make our way to add to waitlist, you can imagine that the file system with the same structure, we'd specify the path, front of house hosting, add to waitlist to run the add to waitlist program. Using the crate name to start from the crate root is like using a slash to start from the file system root in your shell. So we don't have to start from our absolute path, which is crate, every single time if we already know what our absolute path is, you know? Okay. The second time we call add to waitlist and eat at restaurant, we use a relative path. The path starts from front of house, the name of the module defined at the same level as the module tree as eat at restaurant. There are file system equivalent. Oh, here's the file system equivalent in which we'd be using path, front of the house, hosting, and add to waitlist. Starting with the module name means that the path is relative. Choosing whether to use a relative or absolute path is a decision you'll make based on your project. It depends on whether you're more likely to move item definition code separate from or together with the code that uses the item. For example, if we moved front of house module and the eat at restaurant module into a module named customer experience, we'd need to update the absolute path as add to waitlist, but the relative path would still be valid. However, if we move the eat at restaurant function separately into a module named dining, the absolute path to the add to waitlist call, we would stay the same, but the relative path would need to be updated. Our preference is general to specify absolute paths because it's more likely we'd want to move code definitions and call items independently of each other. Alright, so let's try to compile 7-3 and find out it won't compile yet. The errors we've shown are in 7-4. So we have a crate, front of the house, hosting, add to waitlist. This function, add to waitlist, is not publicly reported. It's a private module. So remember, we have to put pub in front of these modules so that we can use them in different files. It is by default private. The module hosting is defined here. So mod hosting. And then we have front of the house hosting, which is a private module. We never made it public, not publicly re-exported. So the errors message say that the hosting is private. In other words, we have the correct path for the hosting module and that add to waitlist function, but Rust won't let us use them because it doesn't have an access to private sections. We can only make them public. Now in Rust, all items, functions, methods, structs, enums, modules, and constants are private to the parent modules by default. If you want to make an item like a function or a struct private, you would put it in a module. Okay. So items in the parent module can't use the private items inside child modules, but the items in the child modules can use the items in their ancestor modules. This is because modules wrap and hide their implementation details, but the child modules can see the context in which they are defined. To continue with our metaphor, think of the privacy rules as being like the back of an office restaurant. In the back office of a restaurant, what goes on there is private in the restaurant to the restaurant customers. But office managers can see and do everything in the restaurant they operate. Now Rust choose to have a module system function that this way they are hiding inner implementation details is the default. That way, you know which parts of the inner code you can change without breaking the outer code. However, Rust does give you the option to expose inner parts of the child module's code to outer ancestor modules by using the pub keyword to make the item public. Exposing paths with the pub keyword. Okay, so here we're actually going to make whatever was private in those child modules public. Now let's return to the error in listing 7-4 that told us the hosting module is private. We want to eat at restaurant function in the parent module to have access to the add to waitlist function in the child module. So we mark the hosting module and the pub keyword as shown in listing 7-5. So we have pub front of house, pub mod, hosting, then we have our function add to waitlist, so it's now public. Unfortunately, the code in listing 7-5 still results in a compiler error. Now, why is that? Add to waitlist is still a private function. Oh. Okay. Alright. Now, what happened? Adding the pub keyword in front of mod hosting makes the module public within this change. Now, if we access front of house, we can access hosting, but the contents of hosting are still private, making that the module public does not make the contents public. The pub keyword on the module lets code in its ancestor modules refer to it, not access its inner code. But modules are containers. There's not much we can do by only making the module public. We need to go further and choose to make one or more of the items within the module public as well. So we would have to make that function public. The errors in listing 7-6 say that add to waitlist function is private, and the privacy rules apply to structs, enums, functions, and methods, as well as modules. Let's also make the add to waitlist function public by adding the pub keyword before its definition in listing 7-7. Sorry, sometimes I just check over here, make sure everything is going correctly. It says everything looks fine, so. Okay. I just like double check, just in case anything stops streaming and I just don't know and I'm just reading to myself. Okay, So we have, there we go. Okay, the errors in 7-6 add to waitlist is private, and all privacy rules apply to structs, enum, functions, methods, as well as modules. So we have to make those specific things public as well. So let's make add to waitlist function public by adding the pub keyword before its definition. So now we have a pub mod hosting, which is public, and pub function add to waitlist as public as well. Now the code will compile to see why adding pub keyword lets us use these paths and eat at restaurant with respect to the privacy rules. Let's look at the absolute and relative paths. So the absolute path, we start at crate, which is the root of our crate's module tree. The front of house module is defined in the crate root. While front of house isn't public because the eat at restaurant function is defined with the same modules as front of house, it is eat at restaurant. That is, eat at restaurant and front of house are siblings. We can refer to front of house from eat at restaurant. Okay, so next is hosting module marked with pub. We can access the parent module of hosting, so we can access hosting. Okay, so as long as you can access the parent module, the child module should be able to access whatever's in the parent module. So finally, the add to waitlist function is marked with pub, and then we can access it in the parent module so the function works because the hosting, or the add to waitlist function was in the child module, and now that it's public, the parent module can access it. In the relative path, the logic is the same as absolute path, except for the first step, rather that starting from the crate root, the path starts from front of the house. The front of house module is defined with the same module as eat at restaurant, so the relative path starting from the module is in which eat at restaurant is defined works. Then, because hosting and add to waitlist are marked with pub, the rest of the path works, and this function call is valid. If you plan to share the library crate so that other projects can use code, your public API is your contract with users of your crate that determine how they can interact with your code. So there are many considerations of how managing changes is your public API to make it look easier for people to depend on your crate. These considerations are beyond the scope of the book. If you're interested in these topics, they have API Rust guidelines. Oh, goodness. I'm going to take another quick water break, and this is going to be our last chapter for today. I think we did 3 chapters, and I think we're at 48 minutes. So I'd like to keep these at an hour. Once we finish this one, then we'll end the video, and then we'll start 7.4, 7.5, and I think is there 7.6? No, 7.4 and 7.5 will be there tomorrow. Alright. Alright, cool. Best practices for packages in binary and library. So we mentioned that a crate can contain both a source / main RS binary crate root, as well as a source / librs library crate root. And both crates will have the package name by default. Typically, packages with the pattern of containing both a library and a binary crate will have just enough code in the binary crate to start an executable that calls code from the library crate. Now, this lets other projects benefit from most functionality that the package provides because the library crate's code can be shared. The module tree should be defined as source / librs. Then any public items can be used in the binary crate by starting paths with the name of package. The binary crate becomes a user of the library crate, just like a completely external crate would use a library crate, it can also be used as a public API. Now, this helps you design a good API. Not only are you the author, but you're also the client. In Chapter 12, we'll demonstrate the organizational practices with a command line program that will contain both a binary crate and a library crate. Now, starting relative paths with super, you can construct a relative path that begins with the parent module rather than the current module or crate root by using super as the start of the path. Now, this is like starting a file system path with a ... syntax. That means that you go to the parent directory. When using super allows you to reference an item that we know as a parent module. We can make rearranging the module tree easier when the module is closely related to a parent, but the parent might be moved elsewhere in the module tree someday. Okay. So you don't want it to be an absolute path because you don't know if you're going to move or it's going to be moved in the near future. Okay, consider the code in listing 7-8 that models a situation in which the chief fixes an incorrect order and personally brings out to the customer. Now, the function fixed incorrect order defined in the back of house module calls the function deliver_order defined in the parent module by specifying that the path to deliver_orders starting with super. So here we have a function called deliver_order. We have mod, our module, back of the house. With the function fix incorrect order, we cook order, and then we're using this super : deliver order to show the path. Then we have function cook order, and then the block of code is done. So the fix incorrect order function is in the back of the house module, so that we can use the super to go to the parent module of back of the house, which in this case is crate, the root. From there, we look for the deliver order and find it, success. We think that back of the house module and deliver order function are likely to stay in the same relationship to each other and get moved together should we decide to reorganize the crate's module tree. Therefore, we use super so that we have fewer places to update code in the future if this code gets moved in a different module. Alright, so making structs and enums public. Now, we can also use pub to designate structs and enums as public, but there are a few extra details to which the uses of pub for structs and enums. Now, if we use pub before the struct definition, we make the struct public, but the struct's fields will be private. We can make each field public or not on a case-by-case basis in listing 7-9. We've defined a public back of the house breakfast struct with a public toast field, but a private seasonal fruit field. Now, this models the case of the restaurant where the customer can pick the type of bread that comes from the meal. The chef decides which fruit accompanies the meals based on what season it is and what stock it's in. The available fruit changes quickly, so the customer cannot choose the fruit or even see which fruit they'll get. So mod back of the house, we have a module. Then we have our struct, which is breakfast. Now we have to make it public so that we can see it, as well as make the fields within that struct public. So we only made toast a public field. You can see that seasonal fruit is not public. Then we have an implementation block, which is called breakfast. We have a function, a public function named summer, using a parameter of string and returning breakfast. So then we have breakfast, which is our struct that we used earlier. We have toast string from toast, which is going to be toast. Whatever's toast as in it's here. And then seasonal fruit is string, which is peaches. Now we have a public function called Eat at Restaurant. We order a breakfast in the summer with a rye toast, so we are letting this mutable variable equal back of house, which is this module that we represented up here. Then we're showing breakfast, and then summer. This public function summer, which is rye. So this returning a string for toast, which is going to be rye. Then we have meal.toast equals string from wheat. So we have meal, let's see, meal over here, that's what the variable that we just put. We're mutating it from rye to, so toast will be equal a string from wheat. So we're changing it to wheat. Now print line, I'd like blank toast meal dot toast, and I'm thinking it's going to be wheat. Oh, why won't it let me? It doesn't even give me my compiled code. Oh, the next line will compile if we uncomment it. We're not allowed to see or modify the seasonal fruit that comes with the meal. Oh, okay. Meal.seasonal fruit equals string from blueberries. So we're modifying something that is not modifiable. Is it public? We're not allowed to see or modify, so it is private. Because the toast field in the back of the house breakfast struct is public, in the eat at restaurant, we can write and read to the toast field using dot notation. Notice that we can't use the seasonal fruit field in the eat at restaurant because seasonal fruit is private. Try uncommenting the line in seasonal fruit value and see what error that you'll get. Okay, also note that because back of the house breakfast has a private field that the struct needs to provide a public associated function that constructs an instance of breakfast. We've named it summer here. Now, if breakfast didn't have such a function, we couldn't create an instance of breakfast in the eat at restaurant because we couldn't set the value of the private seasonal fruit field in eat at restaurant. Okay, because it's not public, it's still private. In contrast, if we make the enum public in all of its variants, then public, and then we need the pub before the enum keyword listing. Okay, so here we have pub enum appetizer, which is soup and salad. Then we have a public function eat at restaurant. We let order 1 equal back of the restaurant, path appetizer, and then soup. And order 2 is doing the same thing where you have back of the restaurant, appetizer, and salad. Because we made the appetizer enum public, we can use soup and salad variants in the eat at restaurant. Enums aren't very useful unless the variants are public. It would be annoying to have to annotate all enum variants with pub in every case. So the default of enum variants is to be public. Structs are often useful without their fields being public, so structs follow the general rule of everything being private by default unless annotated with pub. There's one situation involving pub that we haven't covered yet, and that's our last module system feature that uses the use keyword, and we'll cover use by itself first, and then we'll show you how to combine pub and use. Okay, so that's going to be tomorrow's episode where we're talking about pub and use. If you haven't been following along on this series, I highly recommend going back and checking out my first couple of lives until this live, of course. What else do I have to say? Check out my mini Rust series and Rust projects that are following this Rust book series. If you are on Twitch, so nice to meet you. This is my second time on Twitch this week. I'm going to keep going live on Twitch, and hopefully later on I will be able to re-upload some of my older streams that I was doing on YouTube. I think that's it. I'll see you tomorrow, and I hope you have a great day. Bye.